Good morning. Welcome to today's IEAGHG webinar on the recently published study, Geological Storage of CO2, Seal Integrity Review. My name is Nikki Clarke and I'm the Senior Geologist at IEAGHG, and I'm very pleased to welcome you to our webinar today. We'll be joined by the team at CR2CRC led by David Bason, who I will introduce shortly. Next slide, please, David. So a quick note on the webinar procedures for today. As attendees, your mics will stay muted throughout. If you have a question for the speaker, please add it to the chat box and we'll address these at the end during the Q&A session. Please also note that the webinar is being recorded and will be made available on our YouTube channel shortly after the event. I will begin this webinar by presenting a short overview of IEAGHG, followed by a brief background and motivation to the study. I'll then be joined by my co-presenter David Bason, who will give us a comprehensive overview of the work undertaken by CO2CRC, and he'll be joined by Max Watson, Hadi, Nourollah, Michael Rieger and Geoff O'Brien to dive into some of the detail. We'll then have time for questions at the end, and please put those in the chat box. Next slide, please, David. So the IEA Greenhouse Gas R&D Programme, IEAGHG, is an international programme that evaluates mitigation options for greenhouse gas reduction and has a programme focus of CO2 capture and storage, CCS. It's a collaborative international research programme founded under the International Energy Agency in 1991. And there's a short disclaimer there that shows that we are organised under the auspices of the IEA, but we're functionally and legally autonomous. Thanks. Next slide, please, David. IEAGHG are a members-based organisation, and thanks to their support, we can fund our research activities. And we currently have 38 members comprising countries, companies and organisations. And our members steer the direction of our research programme. Next slide, please. So our mission is to evaluate CCS technologies aimed at reducing CO2 emissions, to help organisations make good decisions, connect people to help collaboration on CCS technology, and share our research with everyone who needs it. And we do that in a number of ways. Next slide, please, David. So our main activities comprise commissioning technical studies such as this one. We have over 300 studies published via our website. We hold international network workshops, which you can find out more about via our newsletter or visit our events page for further details. We host the GHGT conference, which was last held in Calgary last year, and the next one will be in Perth, Australia in 2026. We host an annual international CCS summer school. This year will be held in Regina in Canada, and we have over 700 alumni from 60 countries for that school. We also have external involvement with organisations, and we're active in the UNFCCC, IPCC, London Convention and ISO standards. Thanks, David. Next slide, please. So on to the motivation for the study. Thank you. So containment of CO2 within geological storage site is critical for safe and reliable long-term storage. IEAGHG did a review in 2011 and felt that it was time to revisit this topic. So we commissioned a new study to review advances made within seal integrity, so sealing cap rocks and bounding faults over the past decade or so. So some of the questions posed included, but not exhaustive lists. So what makes an effective seal in the context of CO2 storage? What are the long-term impacts of CO2 on different formations? How do we evaluate, model and monitor seal integrity? How might CO2 interact with faults? What geomechanical aspects are important? What might I expect at basin scale? And what policy and regulatory measures are in place? And to develop criteria for a database of cap rock properties. So we're very pleased that the report has now been published. So CR2CRC were our contractors. It was headed up by David Bason and his team. And it's been published on a website since September. It's available for members only at the moment and will be publicly available from March. So I'll now hand over to David so he can introduce the team who are presenting today. Thank you.
Thank you, Nikki, and thanks everybody for joining today, whether it's the morning or afternoon or evening where you're joining from. My name is David Bason. I'm a senior reservoir engineer at CO2 CRC, and I lead the geological sequestration of CO2 research program at the Otway International Test Centre, which is in Victoria, Australia. So I'm joined today by some of the co-authors for this study. So I'm joined by Dr. Max Watson. Max is a senior manager of technology development at CO2 CRC. He's got over 20 years of experience in CCS, both at CO2 CRC and at BP, where he worked on the Nourollah project. He's a geochemist by background. We're also joined by Dr. Hadi Nourollah. He is a senior geophysicist. He has a couple of decades of experience in geophysics, and he has worked on various stages of the research program in terms of seismic, active seismic, and passive seismic monitoring at the Otway. Also joined by Michael Rieger. Mike is a geomechanic specialist. He's currently working on some of the data that's being generated at our research program at the Otway, specifically some of the distributed strain sensing fiber optic data that we generate at the test center. And finally, we've got Dr. Geoff O'Brien. Geoff has over 35 years of experience. He is CO2 CRC's chief scientist. He's worked for various organizations, including Geoscience Victoria and NOCTA in Australia. And he's really got a passion for some of the regulatory aspects and how they overlap with some of the technical aspects of CO2 storage. So that's the people. More about CO2 CRC as an organization. If you haven't heard of us before, we've been storing CO2 for 21 years. 21 years of proven and successful CCS. So we have at-scale investment. So over those 21 years, for both capture and storage, we've managed to secure over 200 million Australian dollars of RD&D funding and put together some long-term infrastructure at our Otway International Test Centre. Our mission is really focused on accelerating Australia's transition to a low emissions future. We're a not-for-profit. We have many members, and those members help lead our industry research. So we generate unique, real project data at our test site, where we store CO2 in both saline formations and in depleted gas reservoirs. And we have many members, including a number of super majors and companies from other research organizations. We have well-established collaboration between universities, the industry, nationally and internationally. So currently in our recent research program, we have national collaborations with universities such as Curtin University, the University of Melbourne, and we also work internationally with some of our research partners such as Stanford University, Keigam in Korea, and Wright in Japan. As I've mentioned a couple of times, we have the Otway International Test Centre, OITC. It's a globally unique test centre that helps us to put together commercially relevant demonstrations of both capture and CO2 storage in the subsurface. So in the image on the right, you'll see a bit of a cube of the Otway Test Centre. It's heavily instrumented. We have many wells, 8 deep wells that are purposely drilled for CO2 storage research, as well as 4 shallow bores. Many of the wells are equipped with the typical sensors, pressure and temperature, as well as fiber optic sensing, such as distributed acoustic sensing or distributed temperature sensing. So coming up today, we've handpicked a certain number of topics to present on. We don't have time, as Nikki said, to cover every single aspect of the report. So we've put together a few specific topics that we think may be of interest. So Max will present first on the long-term impacts of CO2 on different formations. Then he'll hand over to Hadi, and Hadi will talk specifically about active and passive seismic monitoring in terms of how you use that to evaluate, model, and monitor seal integrity. Then he'll hand over to Mike. Mike will talk about geomechanics, specifically how you might model geomechanics for CCS. And then finally, we'll hand over to Geoff, and Geoff will talk about regulatory, what acts, frameworks, guidelines are in place across the globe, how that works in terms of project rollout for CCS. Before we go into any of the detail with Max in terms of the geochemistry, sort of want to highlight a few points in terms of the motivation for this study. So Geoff will touch on this in more detail later, but really we just wanted to highlight at the outset that the containment requirements for geological carbon sequestration really differ from those from petroleum. So in petroleum, we talk about a seal. We consider a seal to be effective if it retains large mobile hydrocarbon accumulations over geological timeframes. Whereas for GCS, we're looking at an effective seal as simply a state of nature that enables a certain mass of CO2 to be retained within the defined boundaries, both lateral and vertical, of the storage complex for a prescribed period. So for GCS, a seal does not have to be the single lithological unit to be effective. We look at combinations of various mechanisms, structural, stratigraphic, residual trapping, dissolution trapping, and how those various mechanisms minimize the column height of that CO2 and subsequently the buoyancy pressure on the seal. So with the focus on recent research and recent literature for this study, I thought this concept was really nicely illustrated by some work that Dr. Alex Bump did out of the Gulf Coast Carbon Center in the US. Him and his colleagues put together this really nice illustration that shows on the left-hand side what is considered a conventional seal, with that thick seal above as a discrete geological unit. And then on the right, this idea of a composite confining system. So you can see that CO2 building up, and we're not necessarily talking about that single geological unit. We're talking about individual units that may be laterally discontinuous, but together act as this confining system that essentially limits the migration and slows the migration of that CO2 out of the storage unit into the confining zone. So here we're not just talking about capillary entry pressures, we're really talking about how the relative permeability controls the migration, even if it overcomes the initial capillary entry pressure to get into some of the sealing lithologies. I'll hand over to Max, and Max can discuss the long-term impacts of CO2.
Thanks, David. Yeah, just to echo David's point there. So when we're looking at the seal, we're looking at the seal system itself. So it's not the concern of CO2 necessarily just entering the lower parts of a seal. It is it getting through that entirety of that sealing system itself. And when we think about the long-term impacts of CO2 on seal formations, well, look, pretty simply, if the seal performance short-term is good, it's all behaved as we expected, then it's very likely that the sealing system is going to be very good long-term as well. And I wanted to really iterate that point is, so we'll go through and we'll look at some scenarios where, maybe the seal doesn't behave as expected and, what if scenarios, etc. But a well-characterized site with a straightforward and good quality seal system will work well. And when looking at these longer term processes that then can occur and giving considerations to those. But if that short-term system works well, and the team will go through that short-term processes in the following slides, then really what we need to consider is potentially what can happen in terms of CO2-induced fluid rock interactions at that reservoir to seal interface or interfaces, or if there's faults and fractures which can allow some CO2 to enter into that sealing system, as well as consideration of that very slow process of CO2 diffusion into the top seals as well. Sally Benson has drawn this figure on the right, which I think is getting fairly well recognised as a nice way of representing the the likely risk profile of a typical CO2 injection and storage operation. And you can see the majority of risk, and that's risk for various processes, including integrity considerations for that top seal, really occurs sort of throughout and at the sort of the end point of that injection phase, and really tails off quite rapidly after that. But we do need to give that consideration nth time beyond the sort of the injection operation as to what may happen there. Those processes are mostly geochemical processes. CO2 is a reactive fluid. It does dissolve into formation water, and it does change the pH conditions to some extent. And we do need to give that consideration then. If you do have some geochemical changes, that doesn't necessarily lead to any, say, leakage risk directly on those seals. You still do need to consider maybe that geomechanical perspective if you are changing the seal properties in time. Oh, I can't advance. I was pressing the arrow button. David, can you please advance? Thank you. So again, a good thing to emphasize is geochemical changes in a good quality seal is pretty minimal. Now, the reason for that is really that it's hard to get CO2 into a seal. In a reservoir rock, so what you've stored into, or maybe intervals of higher perm systems, if the CO2 is there, yes, it will dissolve into that formation water, and you'll reduce your pH, which can enable dissolution reactions to occur. And those dissolution reactions will yield, say, iron, magnesium, calcium cations. And if they're sufficiently available, then you can have precipitation reactions. And there's a lovely diagram from 1938, Goldich, really identified a weathering system, and the more susceptible to least susceptible minerals for weathering. And weathering, to some extent, is essentially the susceptibility of surface minerals, in this case to rain, and rain being slightly acidic. You're having these reaction series occurring. And we've added a couple of extra series to that with consideration of CO2 storage in geological storage systems, in terms of susceptibility of carbonates, range from calcite, which is quite susceptible, down to things like anchorite and siderite, those more iron and magnesium bearing carbonate phases, which you typically see as precipitating rather than dissolving, particularly in the longer term, as those iron carbonates minerally trap CO2. And then in clays as well, the more complicated and more iron and magnesium rich clays are the ones that typically react more rapidly, while ones like elite and kaolite in particular are a fair bit more stable. And you'll see that occurring if you can get CO2 into the seal rocks as well. But CO2 is really a limiting factor in that CO2 water rock reaction, because it is so difficult to get CO2 rapidly entering into that system. But you can have some things that can assist that entry of that CO2 into the seal, and that may be things like fractures. Now, right now, the ability to model reactions in seals is probably limited or hampered by limited knowledge. So the common mineral phases that you typically see in reservoirs, yes, they exist in the seals as well, but there's probably more complex geology, complex mineralogy in there, which makes it more difficult to really represent accurately in the very long timeframes what may be occurring there. So certainly more effort may be required in improving thermodynamics and kinetic predictions of CO2 reactions in seals in that regard. But it is suggested that you may actually get, in a lot of cases, seal enhancement from precipitation of carbonates in just to really block up what little pore space is available in those seals. But again, you may be altering the geomechanical properties in those dissolution alteration reactions, and you need to understand what those geomechanical properties are like in that evolving system. Next slide, please, David. Now, one thing that we can use to help us understand long-term what's happening in terms of seal quality with CO2 influence to that is looking at natural accumulations of CO2. And look, there's lots of those in reservoirs, so you can find them all over the world. It's a lot harder to find good analogs for CO2 interactions with seal. Oil and gas companies typically don't like to sample seal. They're interested in the reservoir, and really finding seals that you have sort of sufficient knowledge to say that you've had long-term reactions with CO2 is difficult. But there are some examples, and there's the fields in China, the Green River in the USA. One I wanted to focus on a little bit for now is an example in Australia, which is called the Pine Lodge gas field. It's in the Otway Basin, but a long way from our CO2 CRC Otway research facility. So it's right over on the state border between Victoria and South Australia. And the gas accumulation, which is about 99% CO2, actually occurs in a fractured mudstone, a mudstone that's commonly a sealing mudstone for a lot of natural gas accumulation throughout the Otway Basin. So we were very fortunate to find that the Victorian Geological Society had drilled this well and taken full core of that, and basically had not touched this rock. So we were able to get this and have a look at these natural fractures and look mineralogically at what's happened in those fractures and what's happened to the intact rock around those fractures. We took some samples and looked at varying siderite content in particular, and compared that then to the seal capacity analysis using mercury injection type analyses. And what we found was, yes, you'd certainly had CO2 alteration of that rock occurring right next to those fractures bearing that CO2. And the result of that was an increase in siderite content. And as a result of that precipitation event, the seal capacity immediately next to those fractures went up dramatically. You can see those column heights for CO2 storage potential there, varying from 100 or 200 or so over to about 300 meters in the upper zone, and then even more ridiculously high in the lower zones from 600 to 700 as improvement levels. So that suspected sort of improvement or enhancement in seals from alteration reactions was observed in this and some of those other field examples as well. So that was a quick run through of what could happen long term, and some considerations that we've sort of noted in the report into where we need to maybe consider what to do in the future. But again, really want to emphasize, in most cases, it's going to be extremely hard to get CO2 into competent seal for these reactions occur, and those processes are very, very slow and potentially improvement type reactions that occur. David, that's my last slide.
Thank you very much. Now, moving from what Max just explained, how are we going to monitor the seal, especially from a seismic perspective? The two main questions that I normally ask is, how much does the seismic see? And how much does it need to see? Do we need to actually see every molecule of CO2? And even if we do, would it be necessary? How would it impact the seismic? Those two images on the left-hand side in the middle show a theoretical microscopic image of how a seal would look like. A perfect seal would be comprised of clay platelets mounting on top of each other, lying on top of each other, virtually leaving no space to a passing fluid to go through them. Technically, if you want to model them, these pipes, passages, they can actually, those blue pipes, and there are pathways for a CO2, for a fluid to go through these seal. and these shale platelets. On the seismic side, how you would see that is a bigger combination of this. The seismic see what we call an effective medium theory, and a general overview depending on the depth and the wavelength that impacts upon the subsurface rocks to see a combination of the fluids and the subsurface rocks and sand particles, clastics, whatever is down there. Those two images, the right-hand image, they're both from seismic. The right-hand image is a publication Geoff and I put forward from Gippsland, Australia. That's how a seal breach looks like. A gas system is working and what creates a gas chimney. So if somehow we inject into a reservoir and the top seal breaches over geological period, hundreds or tens or millions of years, and that would look like that. The seal breaches and you can see an imprint on the seismic. Hopefully that's not going to happen. But we have a smaller breaches of the top seal that can be detected by seismic. The middle image from Brown, it's another seismic image. It's a famous paper, and you can see some smaller pipes breaching through these strata, and technically you have a seal failure. How much of that really matters? How do we want to measure it? And how does the seismic see? The two bottom diagrams, which I don't expect you to necessarily try to read every detail on them, are from a good paper from Espinosa. Full referencing is done inside the report. What it says, it shows that permeability on the right-hand diagram shows a permeability versus a mean porous space between the typical clay minerals and the clay rocks, montmorillonite, kaolinite, illite, so and so at the bottom left of the diagram versus normal sandstones. You can see there's a huge gap between the typical mean porous space and the amount of fluid that can escape through them versus what can go through sandstone. And that's where we need to focus the seismic to see the bulk of this. How much of that will escape? Well, there is no standard out there. Spinoza suggested 3 kilograms per square meter per year. Other measures exist, and we say 1% of the injection rate per 1,000 years. What it is that whatever fluid escapes through your top seal, whether it's through advection, diffusion, whatever mechanism, it shouldn't be significant enough to be literally detected by seismic and compared to whatever rate that you're injecting and storing in the long period. Next slide, please. To achieve this, seismic monitoring goes down the path of what we call active or passive. What is, or we can just categorize it as more conventional versus the upcoming alternative. And I'm going to explain this. The active seismic is basically when you excite the source, you send a signal, whether you use a hammer or a vibrator or an air gun, you send a signal, a wave, an energy down, and record it through some listening devices, whether it's a geophone, hydrophone, anything like that. These are active and they're more conventional. In the alternative, we try to reduce the amount of energy we put through for environmental purposes, for economical purposes. So we heavily rely on the listening part. This is the passive seismic, so you don't have an active source. This moves on the alternative. On the active source, the conventional would be, as I said on the first line, airlines. You have streamers, hydrophone, vibroseis. Examples of which I put one in the middle picture. It's a picture equivalent to our site at the Otway International Test Center run by CO2 CRC. And these are equivalents of the land vibroseis. They're called SOVs, surface orbital vibrators. They're stationary vibrating points. still considered a conventional, relatively modern active source. In the active source methods, we try to measure the fluid type, that saturation, changes in the CO2 injection rates. If we have enough and high pressure difference, we can detect the fluid pressure and the confining pressure changes. Lucky enough, depending on the conditions and changes of the temperature, we can even monitor the heat flow and the temperature changes. And potentially, there has been examples in the industry, geomechanical deformation and fracturing to a limit. Now, I'd like to go to the bottom part and talk about the passive seismic. The image at the bottom is from Otway International Test Center from our colleagues from Curtin University. This is a publication by Professor Pevsner in 2017. It shows that for a small, relatively small injection of 10,000 tons, the passive seismic can actually hear this, can detect it, the onset of the injection, and you can see it. In this method, you're basically mostly listening. So the injection, whether it makes some changes in the pore pressure or in the subsurface, by those small, tiny crackling, you have such sensitive devices that you can detect this. It is in development every day. There are better research, better methods to detect this signal are coming out, and we're moving forward. But we're not there yet to completely replace the active seismic. We can utilize wave sources, natural sources, ambient sources, anything that actually generates energy and noise at the surface around us goes down there and we can utilize. In between, before we get on to the full step to drop the active sources, due to environmental and financial and operational necessities, we're looking at an alternative source in between. And that's where we have those vibrosides. One example is just those vibrator stations. The other one is a marine vibroside that's in development. There has been examples in the past, but we want to move away from the loud pops, those that are generated by air guns, dynamites, and move into more humming sounds that are more friendly to the sea life. And that's where we're moving towards a marine vibroside. And they're getting more developed to fill this gap between the more conventional, very effective source, but for better environmental purposes, until we reach that era and those years that we can completely rely on passive seismic to monitor the injected CO2 plume. Next slide, please. I'm going to make this one shorter in the interest of time. This is an example. There has been many examples introduced in the report. I encourage the viewers to have a look at them. But this one is from the Otway International Test Center from CO2 CRC, which is subject to many types of research and experiments there. Essentially, what we are after in our monitoring, we have to tick 3 boxes. It has to be cost effective, fit for purpose, and being environmentally friendly. In these, we have developed over years of experimentation and field tests that fiber optics are a key element in detecting seismic signal and utilized for long-term reliable monitoring. They can be deployed at surface, inside the wells, behind the casing, over production tubing, or you can just hang them inside the well and record data over decades, very reliable. Different methods, they can detect whether they're Rayleigh or whether they're Brillouin or Raman. They can detect temperature, acoustic signal, or changes in the strain sensing, all of which are deployed at our Otway Research Center. The image in the middle at the top shows that these SOV stations, those small dots, are being excited and in operation 24/7, and the signal is being recorded through the 7 or 8 wells that we have around our site. And those cluster of dots actually show the 2D trajectories between all of these SOV downhole pairs. An image at the top right shows, and one of the wells, a cluster of these images around the well that cover at critical angles, and we can see the changes every 2 days. We basically have one of these monitoring images. We can see and monitor tiny little changes of the plume and how it expands in the subsurface. On the passive side, when the SOVs do not work, we do not operate them at night, and in between their operation, the fibers are still listening. And our friends from Curtin University, that's a result of a stage 3 experiment at the bottom right. You can see that different stages of plume could be monitored passively, and we've detected small seismicity, very, very, very small seismicity events that could be related to one of very small faults in the subsurface, or the interaction of the plume with the subsurface images. Shows a lot of advancement and exciting results from the passive methods, and they are still ongoing in our current experiment, stage 4. I think I'll stop here and pass over to Michael for geomechanics. Thank you very much.
Thanks, Hadi. Yes, I'll be covering the section on geomechanics, and I'll try and run through what its role is in ensuring seal integrity, and I'll also be touching on some of the current approaches for addressing geomechanical risk to CO2 containment. So I'm going to start with lesson 1 in geomechanics with a definition. So geomechanics is a study of how materials deform or change under varying environmental conditions, such as with changes in temperature or changes in pressure. So this is really critical for us to be able to understand how the Earth's subsurface will respond to the injection of CO2. So to be able to do that, first we have to characterize the geomechanical properties and also the in situ stresses or the forces which are acting on the subsurface geology. So the graphic that I'm showing here just demonstrates how we might start to begin to understand those geomechanical properties for any given storage site. So just to quickly explain the graphic, so we have I guess what we could call a conventional anticline structure here, where we've got our reservoir, which is porous and permeable, and overlying that we have an impermeable seal. So we can start to, yeah, there it is there. So we have also an injection well, which is sitting on the crest of this structure. So that injection well really provides us a window of opportunity to start to make these measurements of geomechanical properties. And we can do that in a direct means of measurement and also an indirect means of measurement. So I think maybe within the interest of time, I won't go too deep into the differences of these types of measurements, but I'll just make the point here that essentially we will integrate these two types of measurements, the indirect types and the direct type measurements. And what we produce is a 1D mechanical Earth model. So what that is essentially it's a numerical representation of both the state of stress of the rock and also the elastic and mechanical properties of the rocks. So we use these MEMs as the basis for conducting any kind of subsequent analysis that you might want to conduct, for example, an investigation of seal integrity. Next slide, please, DB. So rock failure is a key risk to the integrity of geological seals. So this slide, we're showing two types of rock failure. We have fault reactivation, which is where the injection of CO2 causes movement on those pre-existing faults. And we also have fracture initiation. So this is where the injection of CO2 may produce or initiate fracturing within the reservoir or the seal itself. So both types of failure have the potential for creating unwanted pathways for CO2 to migrate along and outside of that intended storage reservoir. So the core concept that's driving both of these types of failure is effective stress. And that's been demonstrated in the graphic down the bottom left and also the equation there. So what is effective stress? So it's the forces that are active in the geological system, and when they're in equilibrium, they provide stability to those rock frameworks. And as the equation suggests here, it's equal to the total stress minus the pore pressure. So if we're to increase the pore pressure within the rock pore spaces, the effective stress in turn decreases. And this may push the system out of equilibrium, and it may also become unstable. So if we then take this concept and look back at those two failure types, if we're looking at the tensile failure, this occurs when that critical pressure exceeds the minimum effective stress plus the tensile strengths of the rock. So a reduction in effective stress through pore pressure increase enhances the risk of induced tensile failure. So the failure criterion is slightly different in fault reactivation, where shear failure occurs on the fault where the shear stresses acting on the fault are greater than the effective normal stress and the strength properties of the fault itself. So again, the reduction in effective stress through pore pressure increase enhances the risk of reactivating any pre-existing faults within our system. So to ensure that these failures are avoided, it's essential to have a good understanding of the subsurface geomechanical properties and also the in situ stress conditions. Next slide, please, DB. Yep, so the end goal of any geomechanical study for CCS projects is to make accurate predictions on how the geology will respond to the change in conditions, and also to be able to understand our projects in terms of risk metrics. So the gold standard for achieving this is to produce what we refer to as coupled numerical modeling. So this approach integrates geology, geomechanics, and reservoir engineering data into a 3D model of the subsurface. And using these models, we can then simulate the injection of CO2 into the reservoir. And the coupled model type simulations, they can solve for the interdependencies of the interactions between fluid pressure, stress changes, and strain, for example. So in the middle, we have an example of one of these models, which is actually taken from our site at the OITC. So the front face of the model is a section which is cutting through the trajectory of the wellbore, just so that we can see what's happening at that injection zone. We also have a few faults here, some on-echelon faulting. And the fault to the right of the well is acting as an inhibitor to fluid flow. So this image is just capturing a moment approximately halfway through the injection simulation. And the injection CO2 is visible here as the percentage of gas saturation in the reservoir, which is what the arrow is pointing to. And the background is colored by the change in the pressure which is associated with that injected plume. So as the change in pressure is calculated in this model, the change in stress and strain is also calculated at each time step. And then the fully coupled process, the geomechanical changes then feed back into the calculation of fluid flow. So by capturing the interdependencies of the fluid flow and the geomechanical response, we're able to more accurately reflect the stress conditions that are imposed on the faults that we've modeled in that system. So this is just an example of coupled modeling, but we can also include other processes such as the impacts of temperature, as the temperature differential between the injected CO2 and the temperature of the reservoir. And we can also include some of those chemical processes which Max talked about in the earlier part of this presentation. So ultimately, this approach, it enhances our ability to more accurately identify potential risks to the seal integrity, and also enhances our ability to design safe and effective storage systems. And with that, I'll pass on to Geoff.
Yeah, thanks, Mike. In the interest of time, because we're sort of pushing it a little bit, I'll try and push through this fairly quickly. And before I start, I have to say that I'm here because, unfortunately, Simone de Morton, who's principally responsible for this work, could not be with us today, and she sends her apologies, but she's got a few things happening. And so basically what I'm going to try and do is just provide a really simple overview in the next 5 minutes of the regulatory frameworks and how seals might relate to them, and a little bit on what's happening internationally with these things. And because I've got 5 minutes, I'd advise you to read the report because there's more detail in it. But what we can see here is that there's a triangle, and you can see we've got the Act and the regulations and the guidelines, and these are called different things in different countries. But basically, the Act is the legal foundation for the regulatory framework, and then the regulations sit on top of the Act as usually as a separate piece of, well, as a separate piece of legislation, and they provide in a way, the principles that someone should follow to be in accord with the law. And then finally, we have guidelines, and unlike regulations, which are legal and binding, guidelines are not binding documents. But my experience as an ex-regulator is you don't follow them at your peril. So that's probably how I would describe them. But they're sort of how to do stuff, really, rather than anything else. Next slide, please, Dave. And so what I've done here is just really quickly is to say, well, people talk about this. They say that petroleum and GHG, CCS are similar. Well, as a geologist who's been heavily involved in the petroleum industry and CCS and in the regulatory side, I'd say that is simply not true. That's what I would say. And if you believe that and follow that line, you can end up in some significant trouble. So, for example, with seals, all we care about are, do the seals work well enough to trap commercial volumes of hydrocarbons? And we may well never know what the exact trapping mechanism is. In GCS or CCS, the regulations demand that you understand the trapping and sealing mechanisms. And we can make statements that the CO2 plume should not leave the permit, migrate out of the storage formation, etc., etc. So the bar that's set for GCS is actually much higher than it is for petroleum. And then you have over the implications, well, you can't have the plumes leading permits. The boundaries of the permits become no-go zones. And unlike with petroleum, the plume in CCS expands with time, whereas the hydrocarbon pool will shrink. And then we go through the different phases of exploration, appraisal, and then production to abandonment. And all the way through this, as I've listed, you must understand how the seal is behaving dynamically all the way through the process. And that, again, is very, very different to petroleum. Next slide, please, Dave. And this is sort of, a lot of detail here, and I won't go through all of it, but it's to show that with seals, all the way from phase 1 through to phase 6, seals are a key part of what we need to understand from a regulatory point of view. And I would argue that as a geologist, we all get obsessed with geology, we get obsessed with detailed evaluations of seals, and we do this, but none of it counts unless we can demonstrate that we're in accord with the regulations. And I guess that's my later in life nirvana that I've come to. And so really, you've got to be looking at seals purely virtually purely in relation to the regulatory requirements. And so if we just look at phase one, then that's really the screening start, the very beginning of a screening process for looking at an area. And we might identify seals in that for GCS, but it's going to be based on really limited data. And if we take two examples, if this is saline aquifer, which is the majority of storage resources worldwide, we don't know much about the seals in this. And then the question becomes, which I posed through the phases 1 to 6, is do we actually know enough to get a project approved? And I have serious concerns that a lot of our regulators are going to take such a risk-averse and prescriptive approach to these things that we may struggle to get really good projects approved because we can't meet the bar of what's required to really understand seals, because that bar is simply much higher than petroleum. And in the interest of times, I'll just go to the last one. And the what we've attempted to do here, and again, it's very high level, it's more detail, is summarize, well, how do people view seals in different jurisdictions? And the sort of the greenish color is, well, you can see in the EU and the United States onshore, Australia offshore, Canada, everyone's got legislation, regulations, it's got guidance documents, and there is clarity around what a project proponent has to do in terms of seals. I'd probably disagree with this diagram to some extent and say that there are significant issues in the right-hand column, regulatory clarity in all jurisdictions. But if you look at the other areas, people are developing their legislation now. They don't have guidance documents and they don't have regulatory clarity. And this is a problem, but it's actually a great opportunity for the industry to step in and take a role in really providing realistic, practical, pragmatic, and monitorable criteria that the industry must abide by to get projects approved initially and then through time. So with that, I'll probably, in the interest of time, I'll just say thanks very much, and I'll hand over to Dave. Thank you.
And I'll hand back to Nikki if she's online to facilitate the Q&A.
Yeah. Thank you so much for that. There was a whistle-stop tour, and it just scraped the surface of what's actually in the report as well. So I really hope you go read that. And I can see as well online that people have been answering comments and comments. So maybe I'll just kick off. Do please put questions in the bar. I think we've got about 5 or 6 minutes to answer some questions. I just wanted to ask Geoff. So on the basis of what you've just described, and we can see how detailed it is to evaluate seals, you know, and even thinking of saline reservoirs, which might have much less data than we might have for example, a depleted hydrocarbon field. Are the regulations realistic, or could they perhaps raise unrealistic expectations and slow project approvals? Is Geoff there? Perhaps
sorry about
all
that.
of our speakers. Yeah, that's great. No, go for it.
The regulations are realistic in terms of, in many countries, they are comprehensive. But I think it's human nature that a lot of these projects are going to be first of a kind. And because they're first of a kind, the regulators who have vast 100-year experience in petroleum are going to be very conservative in how they view things. And we're seeing that in Australia. You know, formally and informally, we're seeing that. And so I think it's because this game is so different to petroleum in many ways, that we've got the regulations in place, but how you interpret them is the key. And I think that what we have to do. It has to become a dynamic. It's like a dynamic simulation. The regulators have to dynamically engage with the industry so that collectively we learn how to do this better. And that is going to require flexibility and adaptiveness. And to be honest, as an ex-regulator, I'm not sure that we show a lot of adaptability and flexibility and all of those things. So the answer is, I think it's a challenge and it can hurt projects. Yeah, thanks.
That's great. I think there was another question that just came in for you. So how might you suggest communicating the importance of more rigorous or relevant seal assessment to an operator who wishes to convert a depleted field into a storage location, particularly where regulations are not in place or finalised?
Well, yeah. Again, I'm a great believer. I think work with the regulator or the regulator to be. I mean, I think that's the first thing, and have a strong communication between the project proponent and the regulator, and then bring together all of the sorts of data that I would go to then places like Canada and Australia and others, and see what they say about what you need to do, and start to prepare all of that material. That's probably what I would say. I think a lot of the projects in some parts of the world, I think it's going to be a rapid rollout of projects, which I think is great. But I think early engagement with the future regulators or the proto-regulators or whatever they are, and try to make it a learning experience for both. There's a lot of material out there about what you need to do, but that doesn't mean much if the regulators interpret it incredibly prescriptively and in a very narrow sense. And I think that's the risk, as I see it, from where I sit. I hope that answers the question. Yeah.
Thank you, Geoff. That's great. Okay, so I think we've got a question for Mike. So there's a couple of questions here on modelling. So what are the critical data inputs for geomechanical modelling? And what tools do you use to perform the coupled numerical modelling?
Okay, yep. So in terms of data that goes into the geomechanical modelling, to produce an MEM, which is what I explained in the first slide, that requires quite a range of data, ranging from information taken from the wellbore itself, which could be core samples, which then have the subsequent geomechanical testing conducted on it. So that could be triaxial testing or UCS testing, Brazilian testing. We also would require some injectivity testing, which helps us to understand what are the likely minimum horizontal stresses that are active within our field. We also then require a series of wireline logs. So specifically to calculate these mechanical earth models, you need sonic slowness, VP and VS, and density logs. What else would you need? Pressure data. Yeah, so there's a lot of information that goes into these MEMs. And then the next step would be to integrate that information with the geological model and also the reservoir modeling data. So there is a lot of background information that comes together for one of these coupled modeling processes. And the second part of the question, I think, was what tools have I used? So recently I've been using Rockflow Dynamics software T-Navigator to perform most of the coupled modeling processes, but I've also used other tools such as Petrel in the past and other softwares like RockDoc, which is also useful for producing those mechanical earth models and manipulating that data.
That's brilliant. Thank you so much. If I could ask all the speakers to put their cameras on, just to thank you all for a fantastic presentation today. Thank you for your work and your hard work on this. And I'm afraid we haven't got any more time for questions. We're going to wrap up now. But yeah, thank you so much from IEAGHG to the CO2 CR C and yes. Thanks very much.
Thanks, everyone.
Thanks, Nikki.
Thanks,
Thanks,
Nikki.
everyone.
Thank you.